Hi class, welcome to Online EdVantage. I'm Dr. Scott Adamson, and please subscribe to our channel so you can learn more about line integrals. No, there's lots of things to learn, but we're talking about line integrals here today again. And this is a wrap-up of the previous two videos. I want you to just think about what happened. What happened was this. If you have a vector field such that the vector field is a gradient vector field, then what you have is what's called a conservative vector field. Look back at the previous video so you can see how that all played out. So if you have a conservative vector field, then we can apply what's called the fundamental theorem of line integrals. The line integral can be found by just finding the function f, which takes some work. You have to do some anti-differentiation, kind of like the fundamental theorem back in Calc 2. Find the function f that produced that gradient vector field, the conservative vector field. Evaluate that function at the ending point. Evaluate that function at the starting point and subtract, and you can find the line integral. So, should feel like the fundamental theorem of calculus from Calc 2. Now, since the line integral is only dependent upon the ending point and the starting point, what we say is, in the case of a conservative vector field, the line integral is path independent. We have an issue of path independence here because it didn't matter how you got from the starting point to the end point. It just matters that you got there. We're going to evaluate at the end, evaluate at the beginning, subtract, and we'll have the line integral. So in the case of a conservative vector field, the parameterized path doesn't really matter. Now, imagine this, which brings us to a third and really useful result in some cases. Imagine that the path is a complete loop, shall we say. I say loop because it doesn't have to be a perfect circle, but if it was, suppose the path was a complete circle. We started at, say, 1, 0, and we ended at 1, 0 in a conservative vector field. Then the value of that function f at the ending point and the value of that function at the starting point would be the same value. If they're at the same point, we made a complete loop. So the difference between these two functions would be 0. So the line integral would be 0 in that case. So we notate that with the little circle here on our integral of doing our line integral. This would indicate that the path that we're on, the curve that we're on, is a complete loop. The ending point and the starting point are the same point. Thus the difference of those function values would be 0. So suppose you had a situation where you were supposed to compute a line integral. You had a vector field, you had a path that was a complete loop. It started and ended at the same point, and you were asked to find the line integral. Well, if the vector field was conservative, you could just jump to the idea that the line integral is going to be 0. Now, that leads to one question, though. How can we know if a vector field is conservative or not? Well, that's why there's another video. Come back to the next video and you'll see how can we determine whether or not a vector field is conservative before we even launch into all the computations and see if we can make this jump and just say that the line integral would be 0.